Emailing me for a month.
All right.
Not in our case.
So, two things to be aware of that we want to handle from an administrative standpoint. Next Monday, there's the opportunity to tour the site as far as they've made progress to date on the construction project here from 11:30 to 12:30. Are you aware of this?
No.
Perfect.
Now I am.
Good. Obviously meets outside of our class time. Is this something that you're interested in?
Yeah, I'd like to see it.
Maybe we can talk
Yeah,
Strappy
we're in,
into.
That's right before
Are you guys
Stratco
in a class
starts.
at that time?
Yeah, we're
Just-
in building codes until 11:50, and then
Not
we're in
really.
Stratco's class from noon to 3.
Building codes cuts out at what time? What time do we usually get out? Like 11?
11:30,
We can cut
11:45.
building codes and ask Stratco to start late. So Bruce and Stratco's were,
Okay.
Bruce won't be the problem. He's Strapco.
well, Stratco will be fine.
No, I mean if
I'll talk to
he,
him.
if it messes with the schedule, he gets kind of.
Oh yeah, because the 40 minutes of material he had yesterday filled up that 3-hour time slot for him.
I'm just saying.
Hey,
I wasn't complaining.
Me
this is going to be
That
on
was
YouTube
great.
later, so just
You're doing great,
be,
Stratco.
just be careful. Just be careful about what you're saying. Okay, so
Says Stratco's not
so
gonna
I
be
can
on
email
TV.
Bruce and Jim, and I mean I think that regardless of what class it is that you have at that time, I think that it's appropriate
They're
for you
both
to
construction
be.
classes, so
yeah.
yeah. One's the codes class and one's construction admin.
Yep.
Or something. Or
I mean,
job site
even
lab.
if it was one of your general education,
Yeah.
I would be willing to go and talk to your,
I
to
say
your
let's
instructors
just,
there. I mean, this directly relates to the program that you're in. I think that you guys should be utilizing this opportunity to see this stuff.
we should probably just ghost on that class, because they'll end up making an assignment for it.
Not Bruce, but definitely Strapco.
Yeah, Strapco definitely would. Okay. So, okay, so I'll communicate that with Derek. I'll talk with Bruce and with Jim and get that figured out.
Where do you
Do
want,
we need-
where's the meetup for,
I don't know a lot of the specifics for
Okay.
this yet. So Derek's organizing it. He had originally saved 3 groups of 10 students, and I just thought, my goodness, I could fill 30 students just from my classes alone. So,
Sure.
so we'll see what it is that we can do. I also want to get this out there so that the night students are aware of this at all, if they can rearrange their schedules. The second item, I'm trying to angle for the 26th to get out to Moline. And I understand that you have Larrabee's class right after mine. And I've talked with him, and wherever we figure it out, he's gonna shift his schedule. And we're gonna condense those 2 classes to account for the tour. Do you have another class right after Larrabee's class though, too?
we do,
What time does that start at?
12:40.
It starts at 12:40. Okay.
but
So-
it's Jimmy over in, the other building, Manifold.
Okay.
He'll be,
Yeah,
he's all about
us
construction
going out and
management,
seeing
so
What is the class?
environmental
Systems,
systems.
Integrated
HVAC
environment.
and stuff.
Okay.
Alright.
Okay. So I just think that with the length of time that they want to have up there and with time getting back and forth, I don't know that we'll get you back in time for that class. So I just want to make sure.
Drive up there, it's Elk River, right?
So one of the things that I'm talking about with them is they might just send a bus down and ship us back and forth. They sent a bus up to the University of Minnesota Duluth. So, what's that?
But if we're gonna, yeah, it's cool.
Yeah, I'll, look, I'm not gonna force
Mary's
anybody
class.
to drive down here and ride on the bus out there.
I'm good.
We'll set up what the parameters are.
Alright.
I just, if you're going to arrange your own transportation, just make sure that you let me know. I'll send you out an invite once I confirm it with Greg.
Where is it?
It's their Ramsey plant, so
Yeah,
it's essentially
Moline.
Elk River, border of Ramsey.
What plan is this again? I can't remember.
Moline Concrete Products.
Okay, yeah.
Like an hour?
It's probably about 40 minutes door to door. So, but at least his initial plan, we have to finalize things. He and I have traded a couple of voicemails Friday and yesterday. When we were initially planning it, is they'd send a bus down here, grab us, wheel us up there, go through the plant. They're going to bring in pizza, so it'd be a pretty nice little day.
What
I-
time would we do that at the start of this class?
Essentially the start of this class, yeah, because you guys get done with your prior class at 9:30. right? So it'd be about a 9:45, meet at the bus, hop in and go. If it ends up being the 26th, I will likely have to drive separately because I have my afternoon and evening class. I have them at a concrete plant in Richfield. So Larry will kind of be in charge of the bus, so be that
I'll
as
be
it
driving.
may. But as soon as I get that finalized, I'll send you out an invite in Outlook and we'll sort it out from there, okay? So, that handles the administrative items. Sounds like you have some homework questions. So let's take a look at that.
Explain yourself.
So which one would you like to look at?
So,
You wanna look
I
at
said we start with C.
one of the ones from the book?
just see, yeah, because if we can run through this, because the question I have, like I said before, the D that's given is not the D you'll calculate. And if that's not the case, then
What's going on?
what's going on? Because
This is page 412, right?
yeah.
Okay.
So if we can go through that,
So we're going to start out with our loading
I threw my.
and material information from 13.3A, right?
yeah,
Okay, so we have F prime C,
3,000.
3,000 PSI. The yield strength of our steel, 40 KSI. Okay, or 40,000 PSI, right? Let's see. Okay, right, everybody started with this from 13.3A. And 13.3C gives us that our width is 16 inches. And our effective depth is 32 inches,
Yeah.
okay? So step one, what did you do?
Moment ultimate,
Okay, what does that look like? How did you set that up?
1.2 times 60, 1.6 times 90.
216 kip feet.
Okay, so
260.
1.2 times 60 plus 1.6 times 90.
Yeah, 216.
Okay, so 216. Okay,
And then the tension, moment of tension,
okay. How does that
So-
look?
the 216 divided by 0.9.
Yep, exactly. So we want to make sure, remember that we're using our reduction factor, and for bending, compression, and tension, we use 90%,
99, that's terrible.
And then also converting it into inches.
and then moving it from kip feet to kip inches.
Yeah.
Yep.
So that equals 240 kip feet. Times 12 inches over a foot. So yeah. 2,880 kip inches.
2,880.
Yeah.
Okay.
So when you look at the chart for our F prime C and Y, the percentage of steel.
Okay. What do you get for row?
Is that the big R?
That's
Oh,
the-
that.
Our percentage of steel,
0.0437.
0.0437. And A over D.
0.685.
Okay. And your big R.
1.149.
And what is our units on R? Remember? KSI. KSI,
Sorry.
right? Because remember, this is a percentage,
Yep.
right? And then this one would be unitless,
So
right? Because we have inches per inch. Okay? Good?
I solved for D right away, but I don't know how everybody else did.
Well, I plugged in 32 inches.
So I did D
Just kind of where
equals,
it goes to a blur.
yeah, so I did D equals the square root of FT over RB.
Okay?
And that's where I'm getting a separate D than what's listed there.
Sure. So, I guess what I would have you keep in mind here is, here you're essentially given your dimensions, right? So, we don't need to determine that. Now, what you would be doing if you're doing this is, can we economize this beam? Can we make this beam smaller than what it actually is?
Well, if that's the case, then hell yeah.
Well, but keep in mind, it may not always be the case. We don't know why we're provided this information.
Okay, so when the book does give us that D, that essentially we have the formula to figure out the area of steel.
Yep.
So
Yep.
that's where
Yep. Yeah, so at this point, you don't need to figure out a beam depth for it, right? You're given what your beam depth is.
sorry about that, Gilly.
See, so that's why I got 22.37.
Okay?
So what if we, so if we did solve using that formula,
Yep.
the square
So
root,
if this was gone,
yeah, and so I got something very much smaller. I rounded it to 13 inches.
Yeah.
And let's say I solved for that,
12.51.
would
Yeah.
I still be correct in the problem?
I
I economized,
you economize the beam, I'll agree with you on that.
and then I solved for
But
what the hell I solved.
we don't know what the there may be some constructability
I
requirements
guess gotta fill that.
where we have to fill this space.
Well,
Gilly.
So
22.37, bud.
unfortunately for full credit, you will have to rework it with this. But you have a lot fewer steps that you need to make, right?
Yeah.
well, this is like the second time I've worked, so this will be number 3 of doing this problem. So fewer steps from that. So.
The joys of failing safely is that's where you learn the most, right?
I'm gonna need you to push back that turning date.
That'll be fine.
Okay.
Tonight would be.
Push it back to the end of class. Is that what you're looking
Are
for?
we not doing anything after this?
So we won't be testing beams. I should have said that too. That was another administrative thing. I don't have the beam tester yet. So without a beam tester, we can't test beams. So that's unfortunately just going to be in limbo. Jake had actually ordered it because he has the PO for the lab. So I'll check with him again and see where we're at with it, get a tracking number so we can figure out.
Okay.
Because I'd prefer to be able to say to you guys, hey, we're going to test here rather than, oh, hey, welcome. Guess what? It's time to test. You know?
So I think that the big hiccup here too was doing that equation and not getting the D provided.
Absolutely. Yeah.
And
how
I
do you
know
proceed?
I've said to more than one person, I was like, I think the D when you do the equation is the one we use to solve for. So
Yeah.
And when we're setting up these problems, and we don't know this dimension, you're absolutely correct. That would be the method of proceeding.
yeah.
That yes, first we determine that depth and see, and then use that to determine our effective width. But here, we're given our beam dimensions, and all we need to do is figure out what amount of reinforcing do we need to put in to properly support it. Okay?
I mean, there could be a
So-
chance I picked the right bar.
Yeah, absolutely. So, do we need to look at this further, this problem, or do people feel comfortable moving forward?
Yeah, can we finish it out to get the area?
Yep.
And
Yep.
our bars and.
So I was looking for like a reference to like go back to, and it's hard to like go all the way through it when we don't have something to like reference back to.
Sure.
Finishing it out.
Yep, yep. Okay, so knowing what we do know, well, this still would be step 4, right? Okay, so given that we have this, what is our next step?
Area of steel.
We're gonna calculate our area of steel, right?
Yep.
And what is our equation for the area of steel?
The.
PVD.
Yeah.
Nope, rho BD, right?
Rho B.
It would be.
So, here it's just plug and chug, right?
7 times 6, yeah, that's what I got. That's what I got last night when Gilly laughed at me.
Well, you can't, I wouldn't blame him. I think I let him go on their own path there. So I got 42,
22.37.
yeah,
Thanks to the man.
You got what?
22.37.
22.37.
Gone.
Where would you start rounding on this? to be honest with
So I personally, I wait to round until the
you.
end.
To the end, okay.
Yep.
All right.
But again, we have to keep in mind, how are we actually going to make recommendations for this thing? We're not going to tell people that we need 22.37 square inches of steel, right? What happens if you say that to somebody?
Yeah, you're gonna say what the hell you're talking about.
Or they're going to laugh at you, right? They're going to do one of the two things, depending on how well you know them, right? So we just have to be aware that what we're doing in here, we're doing it to a level of precision that we're not going to follow in the real world, right? What we're going to do here is we're going to figure out what's the closest that comes to this that has a larger size. And that's what we're going to use, because we want stuff that's commercially
And
available.
you interpret it into something that
Yep.
is practical.
Is
and makes sense.
exactly. Now, yes, I am certain that the foundries would love to make us rebar that would make this size exactly and give us the number of bars, but now they have to make a different size, they have to reset their forms, that's gonna cost us extra money. Okay, so it's far easier to figure out, hey, what is it that you make that's gonna meet these requirements? Okay, does that make sense to everybody? Okay. All right, so now we have the area of steel.
H.
What do you want to figure out next?
H.
You want to figure out H? What does H represent?
The whole.
Right?
Yeah.
So when we're talking about H, we're talking about the entire beam depth, right? And what does D represent?
The top, the middle of the steel.
Yep. Okay. So, what does the equation for H look like? What is it that we have to take into account?
So D +32
Plus our cover,
Plus stirrup.
plus our stirrup,
Plus half your diameter.
plus half the diameter, right? Because remember, this distance is just getting us to the center of that bar, right? Because that's where we're resolving that tensile force.
diameter here every time.
Okay?
That's really confusing.
We're just gonna use a 1-inch diameter here
I
at a
would,
time.
I would recommend just using a 1-inch. It makes your calculations easier, right? What we actually do when we're working on this is we're gonna have the computer run through this multiple times and do the iterations. But yeah, for the purposes of what we're doing, start out with an assumption that you're using 1-inch bar, okay? So what does that end up giving you? You know what D is, right?
34.375. I don't know if I can just maybe write this one.
Okay?
I think we deal with all the others.
So, now what?
So we take the diameter of bar and divide it by the area of steel.
Take the diameter of bar, yep,
And do some other crazy things.
and what does that number tell us? Tells us how many bar we need to put in, right? Okay? And remember that this one, hopefully we're looking at a couple different sizes, right? So what sizes have you been looking at?
14.
Okay?
So 14 is
Where's that chart?
Yeah,
400.
Page 400?
Yeah,
that's 13.1, right?
yeah.
So 14 is 1.6.
I don't think it's 18. I mean, it's 4.
Yeah, 14 would be
Nine.
1.693 is the diameter.
Which one?
2.25.
Oh, you want the crop, yeah.
You want the cross section, right?
We want the,
Oh, diameter?
Yeah, bar diameter.
we need the
that's
diameter and we need, well, no, sorry, this, our area of steel is gonna come from here, right?
Yeah.
Okay, now, if you want, yes, you could use the cross-sectional area,
I've been using the wrong
right? Wouldn't that be the same thing? If you take the cross-sectional area of each individual bar and multiply it by numbers of bars to get to that number, but you're going to have to do that one step at a time, okay? If you start out by saying, hey, if I know the bar diameter of this particular beam that, or rebar that I picked and just divide it by the total area, you get your number right away. Yes, sir?
Upside down? Shouldn't you have your area divided by your bar diameter?
Square inches.
Number 6? Shouldn't you have your area divided by your bar diameter to
Yeah.
determine your number of
Yeah,
bars?
it should be on top.
Yep, because this is going to always give us a number smaller than 1, right?
Yeah, just write this in there for
I know, problem solved. I know what we're doing. So I skipped this stuff.
22.
It ain't 14 because that gives us 20 damn bars.
Gives us 13.21. That would a number 14 bar.
What? 34.
It's
22.35.
22.37. You gotta use area of steel. 22.37.
Fucking idiot.
So yeah, that would be
Okay, so maybe that'll over.
22.37. So that is 26.
So if we look at, let's just look at 14 and 18. How many do we need if we're looking at number 14?
13.2.
Need 13. How about if we're looking at 18? 9? Does it come out to be over 9?
9.9.
Yep.
Nailed it.
They should use my design with D at 12.5, it's gonna be way cheaper.
Yeah, seriously.
You should what?
Just using D calculated, not. the
Oh,
42.
yeah. Well, and yes, and long term, so you haven't seen these problems a lot, but this long term should throw a red flag. When somebody asks for a 32-inch deep concrete beam, that is going to need a lot of reinforcement. Okay? That is a lot of weight of concrete. Okay? So, but when we look at this, what's the problem that we're going to have here? What's the problem that you're going to have putting?
Wider than your beam is.
What's your effective width going to be on a 16-inch concrete beam?
12 and a quarter?
Essentially.
Yeah.
Yep.
Just at 20 plus, sitting at like 30 inches.
Yep.
So on that, so you take 16 minus, I just did 3.75 because that's
Yep.
2 times,
The
you know,
cover,
you
Two
know what I
times
mean?
you cover, 2 times you
So
stir.
that gives you, what was it?
12.25.
Okay, so you take that 12.25 and just kind of hold it over here, and then every time you come up with whatever number that'll give you, as long as it's lower or close to the 12.25, you hit your number. Or you
No, you
hit,
get it so low for your spacing.
yeah, that's what I'm saying, you divide it and then add
Once
your
you
inches.
figure out, yes. Once you figure out your diameter needed
So,
and your spacing, if that comes in less than your available width, you're good to go.
so we got 13.2 on number 14, right?
Yeah.
Is that what we got?
Yep,
Yeah.
yep,
So,
Roughly, yeah.
wouldn't you need 12 more inches of spacing?
Yeah.
correct.
So,
None of these will work.
Yep.
we're way the hell out.
Correct.
So we have to go.
So you got a value
smaller.
engineering.
So, we
Exactly.
ran out of our table, because don't you need to go larger bar?
So, perhaps, in actuality, what we're going to do is we're going to look at, maybe we
Better
aren't
be
able
bigger.
to do 1 layer of steel. Okay? Maybe we need to talk and figure out why we need 32-inch depth. Okay?
The book doesn't talk back.
I need to
I
get some
understand.
solid answers on these questions, man. Seriously. Like, I would have kept going and going and going and then burnt my book.
For the purposes of what we're doing, if you get to this point and you are not able to solve it with the tools at hand, you just need to say, we either need to use multiple layers of steel or we need to resize the beam. Okay?
For your answer?
Yep,
We didn't go over that in class.
Okay.
And that's the answer to this one then? Just we need to
Yep.
resize it?
that's as far as you can take this problem. We don't have time to look at multiple layers of steel. I mean, if you guys want, as Kurt said, you could go back and you could say, okay, 32 inches does not make sense for this beam. Okay, let's look at what would we actually do. Okay, I'm more interested in you guys figuring out what the sequence of steps is at this point. Okay,
Yeah, you should just assume I did that right off the bat.
I was gonna say.
you
I
saw
was-
it. You saw it. You knew 32-inch beam was too
Yeah,
deep.
so that's why I
So it's more like
refigured for 12.5, so I actually did it right.
Yep.
I oversolved, is what happened.
Shut up.
I want credit for this assignment.
Alright, okay. So
Got all the
do you have
steps
an
in there?
answer? Yeah.
So.
Did you solve for D?
Yeah.
And so then, is anyone having problems with the third problem, the item that I gave you, assigned you to solve? Did you want to look at that one?
The actual solvable.
So would we stop once we figure out D? Because you're just asking for the width.
No one's asking.
Did
No,
I
that's on
also
the-
ask you for
Oh, does it?
bars and spacing?
No, we don't.
Yeah,
You wanted,
I thought it was the homework problems that don't ask.
I just
for
put,
more.
my bars and said. I'd
He
put
asked you
over
for
1
more
inch
on
for
his
space.
question.
I thought he was just asking us for D. You can only do these problems so many times in a row.
Yeah, so you need beams depth, you need the total area of steel reinforcing required, and you need an acceptable number of steel bars.
Okay.
Okay?
That's what I solved through the whole thing, but
Okay.
that's probably the only one I maybe didn't read.
What do you want as far as
Which one?
bar
Number
space
3.
answer?
Because it's the one that didn't give us D, so I used the formula.
Because we never really
Those other
went
ones are gonna have to
through
reword.
as far as
So
solving
what-
the actual space.
Sure.
I just figured all my answers were, they were in between 1 and 2 inches, so I just put it
Yep.
a little over 1 inch.
Yep. Typically speaking, we want to limit it to, we don't want to have the spacing less than the bar diameter.
Right.
And so where we typically start is that we just use 1 inch, if that's going to work. Okay? So, and that just helps to make your calculations easier.
Say you go through and put at 1.56 inches or whatever.
Sure.
So
We never did
Let's-
that,
let's
so
say-
we didn't have to do
What
that.
time you administered it should be?
let's say we were using number 18,
Yep.
right? And it gave us 10 bars.
But we've never
Yep.
done one with
And then we need to add
1 inch.
9 inches, just for 1 inch spacings
Right.
in
Yep.
between the 10. That's it, that'll give us the number we compare against,
Your
the width
available
minus,
width.
okay. So we don't take that plus the cross-sectional area, that's.
Correct.
Okay.
Remember that your cross-sectional area this is your cross-sectional area, right? Everything that's shaded in blue. This is our bar diameter, right? From this edge to this edge, okay?
Yeah,
And when we're dealing with our width,
oh, okay,
we're just dealing
it's
from that
given-
end to that end of that beam.
Okay.
We're dealing in straight inches. Our bar cross-sectional area is gonna be in square inches, right?
gotcha.
Okay?
if we submitted it and we solved for D instead of use 32 inches? SOL?
Better start rewriting it, bro.
Holy shit, 10 o'clock.
Oh, you've already submitted it
Yeah,
and you solved for D on
I
that, on
solved
that
for D in
problem?
the first two.
Yeah, I've already submitted 2 of them, so.
If you've already submitted
You'll
it.
see my
and-
work and
Yep,
it's
yep,
solved. I
yep,
mean, I submitted with all the work and everything.
yep. Yeah,
Anyway.
for this problem, I guess, yes, if you've already submitted it and you solved for D, you step through it like how we did in class, yeah, that will be fine.
I'm sure for most of it's probably C and D that we did that for.
Yep.
Like I said, but
Yep. Okay. Other questions on that homework assignment?
can we get some more?
Can I got one.
Yeah.
When you're converting it from kip feet to kip inches,
Up here, converting from kip, yep.
why are we multiplying it times 12 instead of dividing it by 12?
Because there's 12 inches in a foot.
But so now if you got,
It cancels out the feet.
I'm missing,
In order to cancel out the feet.
so if you had an area and it was pounds per square foot and you turned that to pounds per square inch, wouldn't you change that?
You'd multiply it by 12.
Okay, so,
I'm missing something here.
Yep.
My logic is gone.
that's fine. We oftentimes, and I know I certainly always do, instead of writing the dimensions how they actually appear, I shorthand it to PSI, KSI, things like that, right? But remember that when we're talking about PSI and KSI, the inches here are in the denominator. Okay, when we're talking about bending, remember that we have a force multiplied by a distance. So here,
Okay, now it makes sense.
our length dimension is in the numerator.
I was doing more like a volume than
Yep.
inch.
They would be both over 1 or whatever, right?
It'd be both
If you're to make it a fraction,
Why did you tell me that?
Here, yes, yeah,
to make it more sense.
yes, yep. Yep. Okay, other questions on this? Okay, so does this need to be opened up until midnight tonight?
Yeah.
Okay. Okay, we can do that.
So A.
Do we need to look at another example like this then, to help you with it? Or are we ready to move on?
My only issue was with finding the bars, where to start with that. Or that was,
Locating this?
that was my only problem, why I couldn't get it done in the
Okay.
first place was that.
Okay. Good, yep, just reference table 13.1
Yeah.
on page 400.
I think the book is intentionally making it not work out so that.
I'm
learning a
not
lesson
really
or-
sure. I'm not sure. I know that I will intentionally not use this book in future versions of this class.
You know, like math books, they
Yep.
intentionally make it always work.
Yep. Yep.
I think it, yeah, it seems a lot from us.
So you've been right all along, but you don't come up with an answer, so you figure you're wrong.
Correct. Yep. Yep. No, that's why I wrote out the problem that I wrote out. So,
Gave us a heads up.
hey,
Well, we've also never been
it's
provided.
part of the struggle.
Which kind of threw me,
Sure. Sure.
but it seemed wrong to use that one.
Sure. And quite honestly, sometimes this is what we have to deal with in design, is that sometimes we're given the dimensions that we need to use and we have to figure out a way to make it work, but. Okay, well, if you have further questions, come and see me after class or at some point today. I'll be here all day. The next item that we want to look at, oh shoot, I forgot to print my notes. So I need a minute to print that.
Need a minute to rewrite this. How the hell do you do that?
Isn't it off right here?
Look at what for your F prime C is 4,000, right? And you're 60.
Oh, so
You're on this one.
Oh, okay.
I sent them the next, last class. No response.
Sorry, I need 1 second. I have my example problem, but I forgot to print my notes here.
You gonna redo yours?
Yep.
Are you?
Yeah, it'll take like 5 minutes.
Well, it'll be 5 minutes, it's fucking
But then you're gonna go through all them steps to know that it ain't gonna work.
I should just write it out. Doesn't work next.
So 11.725,
Alright, so when you get here,
right?
Yeah,
alright, so you need that many bar, which is, you always have to round up anyways,
7.
don't you? So that would end up being 5.
Correct. You don't want to round up so you're not short.
So then how do you know if that's right or not?
What figure
If that's the amount that you need.
okay, so you take your
There's
B,
5 1-inchers there. Alright, I'm doing number 3.
take B minus 3.75, that's what you're allowed.
How
Okay,
much minus 3.3 stuff?
3.75, it's 1.5 times 2 and 0.375 times 2. So
That's how much you're losing,
because of the,
covering the syrup.
exactly. Now, when you work out this number 6 here, if that's under that equation, I just B minus the 3.75, you're good, unless you can fit a higher bar number in there.
That's width. That's width.
Okay.
That's what I'm sure. Alright. Oh, so I got 12 inches. Alright.
Okay, so the last item that we'll look at concerning concrete construction, we'll look at foundations.
Totally gonna miss this section.
And our foundations serve 2 functions, right? What do we need them to do?
Spread the weight of the building.
We need them to accept the weight of the building. Yep. What else do they need to do? And Steve, I think you kind of answered both of the items in one statement, right? But so they need to accept that weight of the building, be able to transmit it into the earth, and then they need to be able to make sure that whatever resistance comes back from that earth pressure, they're able to resist as well. Okay?
I don't know what I'm doing.
And so what we're going to look at in chapter 16 is we're going to investigate these loads as they're coming in
So it's fresh in my mind.
to our foundation and the resisting pressure coming back up from the soils. How do we have to size these elements so that they are going to be able to meet both of these criteria? Okay, that's the underlying condition. So, yeah,
Just before we go on,
yep.
wouldn't your dead load be smaller than your live load?
Not necessarily.
Okay. Because on your problem, they're flipped around from every other.
Yep.
moving.
Yep.
I just,
Not
I forgot to ask you
necessarily.
that while you were working on that, sorry.
So it's going to depend on the size of the building. It's going to depend on the area per floor with respect to the height of the building as well. So it's,
But we're going back to like what you said in materials and methods too. Like dead load is what the building's built at. Live load is any movable thing in there. So
Yep.
wouldn't that add weight?
That's what he's saying,
keep in mind though, when we are figuring out our live load does not take into account our building elements. Our building elements are only in the
Okay.
dead load calculation.
Okay.
Okay?
So
And our-
you're not like adding the dead load. to the
correct.
line.
Yeah.
See, that's
The dead load
That's
does
where I
not
was
get
going.
added into the live load.
okay.
Nope. So the dead load is, we're only considering the weight of the building materials themselves.
All right.
The live load is, we're considering anything in the building that is transient in nature. Okay, so If we're dealing with an office building, the equipment that's in the office building, the people that work in the office building, everything that supports those tasks.
All right.
Okay? Does that make sense?
Yeah,
That help
no, yeah, no.
clarify
I
that
was-
question?
I was like, how can you have a dead load, then add a live load, and then
Sure. Yep,
the dead load's less?
yep.
Or I
Don't-
mean, flipped, you know?
Separate items,
Okay.
separate items. Good question. So, when we look at these two forces, if we were to look at just a wall footing, okay, so we have a strip wall, the forces that this footing is going to be receiving is going to put this face in compression, right? Put the top face of our footing in compression from the force of the wall as it's accepting that load. And then from the soil itself, this is also going to be providing a face of compression forces, right? On the bottom surface of the footing. The problem with these forces is this force is going to tend to want to deform the top of our footing upwards, right? And the forces from our building, let's see, let's redraw these actually. I'm not actually going to change them, I'm just going to change the color on them so that the deflections make a little more sense. Since I have a whole brand new pack of markers, may as well utilize them, right? Okay, so while these forces from each element are going to be compressive where they're acting, they are going to create tension faces. What do we know that that's going to want to cause the concrete to do? The concrete's going to want to crack. Okay, so we have to figure out, depending on the sizing of these structures, we may need to use reinforcement. Okay, so the chapter provides some guidelines for what you need to take into account for if you are not going to use reinforcement, and then some typical general guidelines for if we are going to use reinforcement. And we'll see how far we get. We may only start setting up the example problem. So the two types that we're going to look at today, and we've talked about foundation types before. Remember that we have our shallow foundations and we have our deep foundations. What are our shallow foundations? What are we talking about here? What types of construction are we doing?
Like, yeah.
It could be residential.
A timber, a stick building.
Yeah, at or near the surface, right? We aren't having to excavate at deep levels.
Anything in the sun.
And what about our deep foundations? First of all, why do we do deep foundation construction?
To find better soil.
Typically speaking, because we have poor soils, right? We want to transmit that load down to something better, something that's going to give us better resistance. Okay? For our shallow foundations, we'll be looking at strip footings, and I think really that's probably about all that we're going to get to. Just keep in mind that we do have column footings too that we can put into our shallow foundations, but really all a strip footing is just an infinite number of column footings, right? We've just put them all together over an infinite number of concrete pads. So typically speaking, we're going to be interested in what these projections are, these little cantilevered sections of our footing. And typical values are going to be 2 feet for masonry and 3 feet for concrete. If there's no reinforcing required. Okay? But that'll be pretty easy and we won't have to do any calculations, right? So we're probably not going to be looking at those from an investigation standpoint, right? So the other thing to think about is that as these structures become larger and they need more load to put into them, where we start getting interested in, okay, now we have to get our reinforcement, we're typically going to be looking at values of 8 and 10 feet, okay? And remember that this is on each side, okay? So, actually there is a lot less material to cover the foundations.
You might as well just skip it then.
Well, no, we can get into the example. So a couple of you have said that the concept of laying out the steps for solving these problems is very beneficial. Do you want to work through an example? And when we get done with the example, go over the steps that we walk through? Or do you want to lay out the steps and then look at the example?
Example of step.
Do the example and then lay out the steps as we're stepping through them? Cut.
I am open. Yep. It was all gibberish.
Okay, so this follows example 1 in section, I think it's 16.2.
16.
Yep. Yeah, it's in 16.2, so it picks up on page 508. Okay? So we're going to design a wall footing. Okay, so we want to design a wall footing with transverse reinforcement. And what this transverse reinforcement means is we're going to reinforce our footing with rebar, where our rebar is going to be oriented perpendicular to the direction of the wall. Okay, so the wall is coming in and out of the board, right? It's coming out towards you guys, it's going back into the beams that we cast last week. Our rebar is going to be placed in the plane of the board, okay? That make sense? Got it.
Why would you put the rebar
In the footing. Because remember what we said. As we start loading this thing,
Okay.
this surface is going to want to
Yep.
bow out, right?
I'm just used to seeing it running with the footing.
Sure. Well, and there still will be.
Oh, okay.
There still will be reinforcement. Yeah, we still would have. bar that's going to help accept this load,
Right.
right? But we also want to make sure that as this footing is picking up this load continually, that displacement isn't causing cracking within the beam itself, or within the footing itself. Let's see, we also know that our wall thickness is defined as 6 inches. Okay? We know from our geotechnical engineers the maximum soil pressure that we can have is 2,000 pounds per square foot. And the concrete design strength is 2,000 PSI. Okay? Oh, sorry. We also know that we have grade 40 steel. We'll refer to this. And the constructability of that footing looks, it's a little askew, right? So. So the first thing that the first step that you're going to be interested in is we're going to have to come up with an iterative value for the depth of our footing. Okay? We'll go back and check this once we get our width figured out. My recommendation, use values that are easily constructible. Look at 6 inches, 12 inches, 18 inches, things like that. Okay? Something that's easy to use. For our purposes, we're going to try h equals 12 inches. Okay? We're going to assume that we're using normal weight concrete. What does that mean the density of the concrete is going to be? Remember what normal weight density of concrete is? Roughly 150 pounds per cubic foot. Okay? So if our concrete density is 150 pounds per cubic foot, and the depth of this guy is 12 inches, how much weight is this going to put on every square foot?
150.
It's going to put on 150. Yep. Okay? So that means our soil can only withstand 2,000 pounds per square foot. So how much additional weight can this soil pick up from the building? If it's already taking 150 pounds from the concrete.
1,850
It'd be 1850, yep. Everybody see that?
Yeah.
Okay, so we have to make sure that we're taking into account the weight of this footing. If we don't, we're gonna have pretty serious issues. Might not have serious issues right away, but what's gonna happen to this building over time?
Sag.
It's gonna sink right into that thing, right? And if we have differing layers of that pressure, if we're 2,000 over here, but we're building another area 50 feet away that's 3,000, what is our building gonna do? Differential settlement, right? Now we're gonna have cracks in our foundation, we're gonna have cracks in our mortar joints, we're gonna have cracks in our plaster, we're gonna have a pissed off owner, okay? So we have to be aware of what's going on with this stuff. The next step is to figure out what is the unfactored load that's being transmitted down into the soil itself. The purpose, why we use the factored loads when we're doing the structural analysis, when we're above grade, remember, is that we have things like wind, we have snow, we have other things that are impacting it. Once we get down into the earth, we're not going to have those effects, so we can use an unfactored load in our soil. So what is our total load going to equal?
Isn't it 8,700?
It's going to equal the sum of our dead load and our live load. Yep. Okay? Everyone see where that came from? Good with it? Okay. Okay, so here, now we can use our total load, right, the total amount that we're transmitting down into the earth, and we can use our net soil pressure to figure out how to size our width. Okay, so it's just going to be our total load that we calculated divided by our net soil pressure available to us. What are our dimensions in?
Pounds per square feet. Oh, there's.
It's going to be in feet, right? Which is that good or is that bad for us?
Don't you want, well, we were looking at.
We're calculating width of our footing.
Yeah, feet.
Beautiful.
Feet is good, right? That's the dimension that we want to use. If we tell someone to make this thing X number of feet wide, they aren't going to look at us like we came from another planet, right? So, Rush, what did you say you ended up with?
4.7.
4.7 feet, right? Okay. Now, if we tell them to build at 4.7 feet, they might look at us like we're a little crazy, right?
Right.
So,
5 feet.
move it something, yes, yeah, it's going to depend on what we're doing, how big we're actually talking. Yeah, we might say 5 feet, we might say 4 feet 9 inches, right? Okay, so depending on what it is that we're looking at.
That'd be great if that was the end of the problem.
It's not the end of the problem.
Yeah. How did I know?
Wishful thinking, man.
Yep. The next step is
509.
we want to check and see, and I'm not going to ask you to do this on your homework. This is just a statement that I want to make about the example problem that they give you. Let's check what this means against the design soil pressure if we use this dimension. I just want us to look back at what we have. Okay, so we're saying that we're going to put in 8,750 pounds per foot into a 4.75 foot member. That ends up calculating at 1,842 pounds per square foot, right?
And that's under the total.
From a math perspective, we can check that box, right?
Yeah,
That's really close.
From how the world of construction actually works, this should make us a little nervous. We've only got 8 pounds per square foot of
So you
wiggle
check
room
that
with
off
this
the
thing.
net, you're saying?
Yep.
Not your total, not your max?
Yep. Now, I don't need you to check this, right? Because all we did was, we just took this,
Yeah.
and, I mean, we just flipped those sides, right? That's all that we did. There wasn't anything inherently crazy to our math that we did. We have not put any safety into our design factor at all, okay? I'm not asking you to, for your